Okay, so again, I'm Shahar. I had the pleasure of working together with Yonina and Moti about the following problem. The microelectronics industry highly depends on SEM imagery for production inspection. They use in whichever company, Intel, Taiwan, they use SEM images in their production process to inspect and detect defects in the production process. According to Moore's law, the production rate increases with time, and the features dimensions get even smaller in each generation. The inspection technology has to deal with a higher throughput of wafers, with an ever-demanding demand for higher resolutions with better quality. We would like to still use fast inspection times, which means low resolution, and use digital algorithms to enhance it. What do I mean? Okay, so in this case, that's the background of the problem. We have the chip. In the lower part, we have low resolution, which is cheap to acquire, and we can go through a lot of wafers in this way. Each one from a different angle in this case. They're taken simultaneously. And once we detect the defect here, the company, Applied Materials, will invest more time and money as a product of it and detect the defect in a higher resolution. The goal is to take a super resolution of the reference image, which means if we take an image of a valid chip and interpolate it into a high-res counterpart, we'd like to create a super resolution version of it, meaning a high resolution version of the reference without actually investing the time and money by acquiring a valid chip. Those are the given images: the defect, reference, and class. Meaning we got the defect, we do invest money because we want to explore the defect, but we don't want to invest more money in scanning the valid part of the chip. Okay, so if we go back to the problem at hand, we would like to compare apples to apples. High-res version of the defect versus high-res version of the reference. Okay, so how do we do that? We've got sparsity, something you've heard so much about today. Well, the features on each chip, they seem quite simple. They're composed of mostly straight lines, arcs. To our naked eye, it seems like the image is sparse, like we can represent it using a compact set. Every patch we take from a SEM image should be, in our assumption, a linear combination from a compact set. In our case, that's the dictionary, in a very similar manner to what Maor just showed. Our goal, in difference to what Maor just showed, to construct both a high-resolution version to construct a low-res and high-res dictionary versions that will enable us to get a high-resolution version of the reference image. We'll call the high-resolution version, digital version, the super-resolution one. Okay, that's the method overview. We divide it into two parts. The first part is just this cube, the dictionary learning. This part is intense. It will take a lot of time, a lot of computational load, and we invest this process offline just once. Once we learn a dictionary for a specific microchip, that's it. We're done. We can store that dictionary aside, and we can move on to the next steps easily and do them fast, which means both the pre-processing, sparse coding, and eventual reconstruction of the super resolution image, they're being performed live very fast and very efficiently. So that's our methodology by splitting the problem into two steps. One of them is intense, but happens offline, and the other three steps, they're happening online and yet fast. Okay, so how do we build the dictionary that we want to use? We said we want to build two dictionaries, so we'll probably need two images in our case. We take the low-res image, we'll call it YL, and we'll take the high-res image, YH. As you can see, the low-res image is very noisy. That's an inherent problem in our model. Noise is something we'll have to contradict using our model. And we take patches. Each time we take a patch and put it into a training set. In this case, we take a training set, we put a low-res training patch and a high-res training patch and concatenate them. And we move on to detect significant patches that are taken randomly, take another one, and repeat the process n times. If we take a very big amount of sampling set, we're going to get a better dictionary. So this process is not only performed on one image. We're going to take a vast number of images, repeat this process, and create a very big T. The bigger it is, the bigger it gets. This is T. You see it has low-res components and high-res components. It's very big. We take all the patches we can get and put our hands on. Now D, the dictionary, is both low-res and high-res in this case, concatenated on top of each other. And X is a column sparse matrix. In the bottom part, we see the optimization problem. In this case, we would like to solve dx minus t and the Frobenius norm to the order of 2, such that x is sparse. We know how to solve this problem. KSVD, MOD, those are efficient algorithms to give us from this scenario with a given t a very good D dictionary that actually solves and minimizes this expression. So we train the dictionary, we get a very good D. Remember, it's a dual D. It has both low and high components. And that's how it looks for the three perspectives. To the left, right, and top perspectives. We see each one of the patches is paired. It was learned together. And in this case, we can actually map low-res to high-res. It's a map. If we look at this component, it's a line, a low-res line, and it maps to a very nice straight lines here in the high-res. The same for different perspectives. This is from the right. We see a very nice shadow. But if we take it from the left, we won't see a shadow. So it won't be exactly a line. That's a good map that utilizes all perspectives at the same time. All of them are paired. And that allows us a lot of noise resilience in our solution. OK, so once we have a dictionary, that's time for sparse coding. We take the low-res image, YL, and we map it out into patches. Each one of the patches is being represented by one column in YL. We take this YL, and we will find a sparse representation over the low-res dictionary, meaning that we actually solve this problem. We take YL, and we want to represent it with DL. Remember the same DL that we've put aside during our offline training. And we find a sparse X, this time X star. X star because it's a very important X. We'll use it later on in order to solve the reconstruction problem. OK, so reconstruction. After we've found out about this X star, which is very unique, reconstruction is an immediate process. All we have to do is take this X star that solves this problem approximately. It's not exact. It's not exact because we have noise. And in this case, replace the dictionary, put D high, and get Y age. This time it's Y age hat because it's a reconstruction. It's exactly equals to this version. That's the super resolution version. And you see it's quite simple. If you build the problem correct, the patches are paired, everything is structured according to our basic ideas. It's an immediate process, and you get a very good result, according to my eyes, at least. OK, so far it's for one perspective, but I just said we have three. So how do we utilize all three perspectives at once? We can define YI LH as the ith perspective image. And we would like to find a sparse representation that fits all of those perspectives at once. Some kind of X star that knows how to take into account all of those perspectives. And the naive approach is looking like this. Just concatenate all perspectives, take all of those dictionaries, stack them up one on top of each other, and find the best X that represents all of this data. It's possible, but it doesn't work good. This approach is quite naive, it turns out. It poorly performs. Some perspectives are more noisy than others, and we don't take it into account. If we have one noisy perspective, it's going to ruin all of the others. So in practice, we have to solve something like this. We take a weighted approach. We measure the noise level in each perspective, and we put it inside the equations. Each one of those dictionaries and samples, original low-res images taken taken from each perspective is being weighted by a specific W. This W ensures us that better version, if we, in our case, in applied materials, from the top is less noisy than left or right. So we're going to put more emphasis on that, on this perspective to solve our problem. And we find X hat that solves it. In this case, we get those very good solution. We go from the low res to the super resolution. And that's the high res ground truth, if you want, as good as it gets, because this one also has noise. And we measure both PSNR and correlation in terms of image quality. PSNR is defined as the log of the maximum intensity over the MSE of each image. And the correlation is found using a cross correlation between both images divided by their respective norms. And you can see the results. To the bottom, we have the histogram. You can see the low res and high res have very little connection between the histograms. They're very wide apart. If we would just use a naive approach of super resolution, we wouldn't have got anything similar to this. But using our own special customized dictionaries that are dual and map low to high res, we can actually get a very similar histogram, which means we get a very good statistic response in our algorithm. Okay, we have a different set here, just to emphasize the result. It's not unique to one image. In this case, again, we got very good results. We got from 16 to 28 dB PSNR. Correlation went up from 77% to 97, maybe 98%. We can actually zoom in, and those are defects that aren't even supposed to be recovered using our algorithm. If you remember at first, we would like to just find out about the reference image, the valid image, but our algorithm is robust enough to even reconstruct the defect to a very good degree of detail. Okay, so we really went from this image to this one using our dictionaries. We had no prior knowledge of this image. Okay, that just to show you that we can actually reconstruct the reference image. In this case, we can't really measure PSNR or correlation because those aren't the same images. But we do get from low res to super resolution, and that's the final goal. We have super resolution reference image, we have the high res defect image, and in this case, Applied Materials has algorithms and engineers that can use computer assistants to detect exactly the defect and tell Intel, tell Taiwan Semiconductors where is the problem, what do they need to change in their production process, and this thing actually worth a lot of money. Okay, that's the summary of our results. You can see both left, right, and top both get a very nice result in super resolution versions. And I think that's about it in terms of results. If you don't believe me that it works for all of the images, we've done an experiment. We've learned a dictionary over 5 images and used the dictionary in 30 different images. You can see all of the PSNR results are quite consistent. We get around the 30 dB PSNR, which is sufficient according to Applied Materials to take into account their automatic algorithms to detect the defect. Okay, so if to conclude, our main contributions in this work, the reconstruction in a joint fashion using a weighted approach is something that really helped us to take into account a lot of noise in the images. We use a very smart adaptive thresholds for sparse coding, and they're fast, thanks to batch OMP, shown by Rubinstein et al. And eventually, we have intelligent overlaps of each patch. We choose the representation of the vectors YL and YH in an intelligent manner, so we can improve performance for very noisy, low-res images. To conclude, our results are satisfactory, and we're very happy about them. I think it's worthwhile to say. It's a significant improvement to current solutions that are being used in the industry. We still need to improve the method in order to achieve great results even in more complex microchips. Those microchips we've just shown you, They're not confidential. We can show them in each conference, but in reality, some of the geometries and microchips today, they're more complex. So we need to adapt our algorithm, improve it, so it will work on more complex samples. And that's it. Just some references that I took. All of those images were gratefully provided by Applied Materials, and I would also like to thank the Metro 450 Consortium for funding the project. We also relied on a lot of foundations, thanks to Aaron et al., Zaid et al., and Rubinstein et al. Thank you very much for the talk. Okay.